Okay, so let's begin to recall. We were in our last, so our module, the current module that we are working on is of trees. In our last class, what we saw was introduction to trees. So we saw tree as a data type and we saw how to interact with it, different terminologies, we defined it, and what do they mean? We understood that. Then we saw different tree traversal algorithms. Particularly, we saw in order, pre-order, and post-order. We saw different applications of tree traversals. We discussed applications like counting number of leaves and a couple others. We also discussed why we cannot apply the graph traversal algorithms directly to tree, or why we actually can apply, but we don't want to because we have something better properties of trees. Can I request, if you are not speaking, then please mute your microphone because there is some background disturbance. I would appreciate if people can do that. Thank you. So where was I? Yes, we discussed the pros and cons of why don't we want to use the graph traversal algorithms like DFS, BFS while we are parsing and traversing to trees. And how can we actually take advantage of the properties of the nice tree and then come up with a better algorithm? And that's why we came up with three different algorithms: in order, pre-order, and post-order. So this was the story we covered in the current module until now. One of the questions that I think could be useful to even people who didn't ask question over email after watching this module was, what is the complexity or asymptotic higher upper bound, big O complexity of these three algorithms? Now, we already discussed the complexities of graph traversal algorithms, both DFS and BFS. And in the lecture, we said that, okay, we can take advantage of the binary tree properties and we can come up with a better traversal algorithm because we know that there is some way or some characteristics that the tree has. So we can take advantage of that. Every tree has just two children, and that's the one of the best characteristics. While if we use graph traversal algorithm, that doesn't take advantage of that property. So the new algorithm that we came up with, we call that, okay, they will have better complexity. That was the whole goal. But then what is actual complexity of these three algorithms? So if we just look back at the algorithm, okay, let's take the post order traversal. All we discussed all three algorithms. So in this, when you see, if you are analyzing the complexity, then you what you notice, or what you should notice to analyze the complexity, is we are taking input of the tree, right? Tree is signified by pointers and some information. So it has pointers to left child, right child, and it has some information in its node. Then what we are doing is, this is a recursive algorithm. We are recursively making a call to the function itself passing it the left child. And then we are making a recursive call passing it the right child. Now, during this recursive call, if you do the scoping rule, I guess everybody knows by this point what is the scoping rule, the box plot for recursive algorithm that we have been practicing since we started doing recursion. So if you do the scoping rule for these two calls, you will notice that every time we are calling each node, so in a tree, visualize the left child, in the left child, then from that node, we are calling its left child, and so on and so forth recursively. But every time you are calling just one node for one time. In the same way, when you do the second recursive call, you are not touching the nodes that you called in your first recursive call, but rather you are touching all new nodes and making recursive call through them, parsing the right-hand side of that tree. And finally, this operation is just in your in order, pre-order, and post-order traversal. There is some operation which needs to be some processing for the node itself that's at hand. And here in this case is just printing the value, right? So this operation is just of constant cost. This operation and this operation, operation 1 and operation 2, this both collectively, when you go through both of them, then you can ensure that you have gone through all the nodes of that tree, whatever was passed as an input argument. So because we are going through each node only once, that's how this both step collectively account for big O of n, where you can say n is the size of the tree or number of nodes in the tree. And big O of n and big O of c, the total algorithm accounts to big O of n. So all three, in order, pre-order, and post-order, all three algorithms have the big O of n as worst case complexity. Now, if you remember the worst case complexity of DFS and BFS, that's definitely higher than this. And that was the whole point of coming up with this new traversal algorithms. Okay, so it was good to get questions. When we get questions, we all share some new knowledge. So today, what we are going to discuss is particularly, now we are going to further dive into the third category of trees. We saw trees in general, then we saw binary trees, and now we are going to dive into binary search trees and discuss more about that. This data type is also popularly known as BSTs. So sometimes you might come across people talking, oh, let's assume that there is a BST or BST can solve this problem. So if you come across BST, that stands for binary search tree. We already defined what is binary search tree in our introduction to trees class. Does anybody remember what is binary search tree? Anybody?
Isn't it like how a tree that has different like childs, and like you have to separate each child on like there's different branches, and each branch has a child, and the other child also has another child. So like it's different branches consisting of different childs. Like each child has a different child.
True, that's a tree, right? Every parent and the child, that structure is a tree. There are some constraints we applied to the tree to define binary trees. And then we applied some further constraints to binary trees to call it as binary search trees. If you don't remember, yeah, go ahead.
All the values in the left subtree are the smallest, and all the values in the right subtree are the largest, right? That's how the main rule.
Correct. Yes, perfect. Okay, thank you, Rohan. So binary search tree, we applied, the tree is the structure where there is parent and child, right? Anything that can be a non-cyclic graph with parents and childs as node, that we can call as tree. Now we applied constraints that if every node has not more than 2 children, then we call it as binary trees. Then to binary trees, we further apply constraint, now not in terms of number of children, but rather in terms of what each node can store. And we said that if every node, if the left child of every node is always smaller than the node, and that property is applicable recursively to every node in the tree, and the right child of every node is greater than the node itself. Again, if this both property is applicable recursively, then we can call it as binary search tree. So binary search tree, if you nicely draw it on pen and on paper with pen, and then you divide into vertical columns, the binary search tree by nodes, you will see that if you go from columns from left to right, the values in the node, they always need to increase because left child needs to be lesser than the parent, and parent need to be lesser, and everything on the left hand side of the right child, right? So right child is always greater than the parent. So that's binary search tree. Now with this recall, today we are going to see further different algorithms of binary search tree. And as you know, I am a very application derived person. So first we are going to take an example. We are going to take an example problem, and then we are going to see how we can solve this problem. Now, until now, you know many data structures, right? Right, starting from array, linked list, stacks, queues, many other data structures we learned until now, different data structures with graphs, trees until now. I want you to think in this problem, how can we use different data structures that you learned until now? And then together we'll formulate different algorithms of binary search tree by working towards solving this problem. So problem that we are going to discuss today is runway reservation problem. Now, this runway is not the fashion runway, but this is the airport runway that I'm talking about here. Miami Airport, that has, I think, 4 runways that we have here at Miami International Airport. But in our problem, we are going to consider this very basic airport that has just one single runway. And runways, as you know, basically they are meant for flights to land and take off, and flights cannot land and take off without the runway, right? So our problem is to design a scheduling system for an airport, not as advanced as Miami International Airport with 4 runways, but our airport just has one single runway for us to make things easier when we are starting with. Later, I think once you understand this scheduling problem, you are able to solve for one runway. I think you guys should be able to solve it for multiple runway airport system also. So what we are considering here is, so we have this airport with just single runway. And whenever the flight wants to land or take off, flights need to, each flight need to make a reservation request to this airport. Now, as I said that this airport is very naive. Unfortunately, it doesn't have like prior schedule, and it is making its schedule online as it goes. So if any flight wants to land, the flight sends the request that, hey, I'm planning to land at this time, can I land or not? And as an airport scheduling system, the job of the system is to either schedule or say that, oh, sorry, that time is not possible. Either there is some another flight or there is a conflict. So to say yes or no to that flight, that can that flight land or take off at that time, or it cannot. So what we are doing is reservations for future landing or takeoff. What request is sent, or what the system is supposed to do, is reserve request specified landing time. So any request needs to be accompanied with a timestamp, and that timestamp is what we are reserving. That, okay, this timestamp is reserved for this particular flight, because as you know that on one runway, 2 flights cannot land or take off at the same timestamp, right? Or definitely, I don't want to be in that flight if that's happening. So we need to design a data structure which deals with such a scheduling, and different operations that we want to do on this data structure is like add T. Let's call this data structure just DS, or let's call it a set. Let's call it a set, set R, something like that. So we'll be adding the time T to the set R if no other landings or takeoff are scheduled. So definitely at the same time, you cannot have two flights landing or taking off. But apart from that exact same timestamp, let's say the timestamp is, what's the time now? 9:45. So let's say the timestamp is 9:45 for that flight to land. But definitely there might be some time before and some time after, right? It needs to run on that runway. So it might take some time, and it needs to be pulled over from the parking space of the airport, and then it needs to be like brought to the runway, and then it like warms up and it ons the engine. Luckily we are not staying in a place where it snows, but in most of the states in US, as you know, this November and December are the months where it snows. So even there are other operations, like airport staff needs to defrost the fans, and they need to like do some things before the flight can actually take off, or flight after it lands. They need to like maybe do something with the wheels, or just to like wrap it in something warm, such to ensure that the cold exterior weather doesn't like freeze the wheel rubber or something like that. So it takes some more time than that exact timestamp. Like 9:45, you cannot say that, okay, 9:46, you can land another flight. So because of that, let's say that that extra time or the buffer time that we need for each flight, if we schedule a landing or takeoff request, is K minutes. So we want to add to the set R if there are no landing or takeoff scheduled in within K minutes. So K minutes before this and K minutes after this. If there is no landing or takeoff schedule, then we can successfully schedule this new request. So T minus K and T plus K, there should be nothing within that. Anything after that, that's fine. Scheduled within K minutes. And K here is just any whole number or any non-zero number. So anything from 1 to anything greater than equal to 1. Sorry, not smaller than equal to 1. Okay, any questions on the problem itself? Everybody understands the problem? Because if you don't understand the problem, then definitely you won't understand different steps we discuss further to solve different constraints of the problem. So if you have any questions on the problem, this is the perfect time to ask those questions.
I have a question, Professor.
Go ahead, Ricardo.
So is it general to solve any problems, like for example, this runway with a problem statement, and then like we solve that problem before coding?
So I don't think I got exactly what you're asking. So are you asking, is it, so your question is not on this particular problem, right? You are just generically asking the process of thinking, I guess. Can you just explain a bit more?
Yes, like, so if your approach with a problem to create application, is it normal practice to create a problem statement first, like how we did in our class, and then solve that problem statement before writing the application?
Yes, so problem statement, it could be either given to you or you are making it from the real life situations around you, right? If somebody could just ask you that, hey, can you please design, like tomorrow you might be approached for an internship at Miami International Airport, and there might be like, we want some software engineer to design airport scheduling system for you. Now they don't know exactly the specifications of the problem. Their problem they just gave you is design an airport scheduling system. It's your job to break it down into something like this. That's what we are doing here. So it's your job to break the problem down into exact specifics. But then our job is not quite done. So you can't directly jump to write an algorithm. You can't just start with hash include stdio.h. You need to
Okay.
first formulate the algorithm itself, right? You can't start coding until you know what you are coding for. So as I
Right.
think we did in most of our topics when we discussed until now, we first formulate the algorithm. We first come up with the logic behind solving the problem. Then after we have that correct understanding of the logic, and if as a human we can solve the problem, we know how the approach of solving the problem, then we write a pseudocode. That pseudocode need not be any language specific. That's just basically a more computer related solution. So maybe you break it down into some functions, some input arguments, some variables, those type of things. Once we have our pseudocode ready, then we take our pseudocode and then make it into a particular language related code. So there's like 3 steps you got to follow. Algorithm is just the logic where a human is able to solve the problem taking different logical steps. Then the pseudocode, and then the final C++ code or Python code or whichever language is your favorite. Pseudocode you can convert into any code that you want.
Perfect. Very clear for me. Thank you.
Okay, so let's take an example for this airport reservation problem that we are dealing with. So let's say that, let's change the color. Let's say that this is our timeline and this is now. Let's call our time as, okay, let's just use the normal time. So now is what, 9:50, 9:55. Right, we are using a 24-hour clock because AM and PM, it might be a bit tough. And then you have, then on this timeline, there are some, at any given point of time, there might be some request that's already pre-scheduled. So let's say some flights are already pre-scheduled to be landed or land or take off from our runway at some time, say some time, that's your favorite. When do we, let's take 10:30. Let's take, let's not take so far. Let's take 10:35 and 10:41. So some flights are already scheduled. Like you got the request early in the morning and you already put them on the timeline. Now, when you were putting all this flight, definitely you were checking the constraint. Every time you get a new request, you were checking the constraints that we have here. But for some of the initial requests, like if now it's 9:55, and if you got a request, let's say that if our K is 3 minutes, right? Every flight needs a buffer time of 3 minutes before and 3 minutes after it to be cleared, and then only it can land or take off. Then if you got a request for 10:30 flight, so 10:30 is definitely more than 3 minutes away from now. And if you, at that time, at when you were scheduling this flight, you already had this flight 1 and flight 2 already scheduled on your timeline. So what you did is you checked that, okay, if 10:35, is it more than 3 minutes away from whatever this new request came for, 10:30? It is, in this case, it's 5 minutes away. And then that's where you were able to schedule a 10:30 flight. But now say there is one more request, and this request is of 10:28. So now when this request comes for this flight, you will check, is there anything 10:28 plus 3 or 10:28 minus 3? Is there any other flight that's already there? And when you check that constraint, right, when you put 10:28 on the timeline, it will be somewhere here. And when you check that, this, yeah, there is a flight which is lesser than 3 minutes away from 10:28, right? This flight, and this flight is already scheduled before this fourth request. And that's the reason you will say that, oh, sorry, on this runway at this point, we cannot schedule this request. Please find some another airport, some another runway to land. I'm glad that I'm not on that flight, which needs to shift from one to the other city just because the runway landing is not available. So, but this is the problem that we are dealing with. So our scheduling system will get this request, and we are supposed to decide if we want to add, first we need to search that do we have any other flight in +3 or -3? Here K is 3 flight. If not, then we add that into our schedule. So we add that to our timeline. If we have any other flight within that constraint, then we just reply that sorry, we cannot add, and we proceed to the next request. So, okay, now with this being a very detailedly explained problem, what data structure do you think we want to use over here?
I think a queue.
You think a queue? Can you
Yeah.
just explain why are you thinking queue would be a good data structure here?
Because there's an order to the way the flights are scheduled, and there's when you label 10:35 as the first flight, 10:41 as the second flight, 10:30 as the third, and then 10:20 as the fourth. So you want first in, first out. You don't want first in, last out. So like whichever flight is first, as long as it meets the criteria of the buffer time, it gets like it's the first element in the queue. Then the second flight, if it meets the criteria, it's the second element in the queue, and so forth. So I was thinking from that perspective. Yeah, like in the or how you put the flights like in a like scheduling order, but from that perspective, yeah. As long as the buffer time criteria is met of 3 minutes, buffer time, that criteria is met. Yeah.
Okay, hang on with me. Maybe I'll let me share some more information about the operations, and then might be your opinion might change. And I also want everyone to think about this. Okay, so I want answers from everyone. This is one of the most interesting way of learning something. We are taking a real problem. We are trying to design our data structure and algorithm for that. And I want everyone's participation in this efforts. So now for this problem, if we look at the operations that we need to do, right? Let's logically list down the operations that we want from this data structures. And then depending upon the complexity, the data structure that allows us to do these operations with minimum cost, that's the one we want to pick, right? That should be clear. So what are the operations that we want to do? First, we want to do insert, right? Every time if any flight satisfies the constraints, whatever the constraints as the problem define, then we want to insert that thing to our data structure. Second, we want to check, because we need to apply some constraints, and for that constraints we need to do some check, like either is there any other flight at the same timestamp? Is there any other flight at the this timestamp -3 minutes, or this timestamp +3 minutes? So that's our check. Do we need to do any other operation? Is there any other operation that we want to do on this data structure?
What's the operation? But do you want to print something out, like saying like, oh, if the flight's not met, if the buffer time is not met, then you say see out, sorry, flight can't be, you cannot land a runway. Like, does that count as like an operation or not really? Just I don't know. That's more like I don't know.
Yes. So let's say we do a check, and then after a check, either we insert, right? If there is a no conflict, then you insert. And you say successfully scheduled, right? You need to give some green signal so that maybe the pilot of the flight can actually proceed with the landing protocols. But if there is a conflict, then you print some message, like you say that, hey, sorry, we cannot land at this time for this flight. So please either make another request for another time, or this airport can't serve you. So then you just see out something. But that both is a part of check, right? You check it and then you are saying either no or you are saying either yes. So you are just like printing some information. So it's like that. So that comes under a check operation. Insert is when you want to add some new element to our data structure. In this, usually what are the operations that we do? We add, we delete, we modify, and we check, right? These are the most common 4 operations we do on any data structure. So in this case, our insert is kind of like insert / modify, right? Because you are not in every time you insert, there is some data already there in the data structure, and you are not deleting, because if there is this flight 1, flight 2, and flight 3 already pre-scheduled, you cannot say that, oops, I forgot that. And now, sorry, I forgot the previous information, and I by mistake scheduled a new flight, and now you're going to crash. You can't say that. So our insert is kind of like insert / modify operation. In this case, we need a check. Do we need a delete in our operation? We actually don't need a delete unless we are running like out of space, right? Because this database, consider this as a database, right? A data structure, just a data structure that you are storing persistently. Then in that case, this will keep on increasing as day grows, right? So after maybe, let's say after a week, the size of the data might be so large, but not all this data is useful, right? Like today, if you are scheduling the flight for today, then all the data until yesterday, they are not useful, because no pilot or no flight can come and say that, hey, I want to schedule a flight to land day before yesterday. Sorry, we can't go back in time unless we have like time machine invented, which we don't have until now. So that's not possible. And so maybe we want to do a delete operation where we want to delete history after some time. Like we want to save it for our log and check something, some data or something, like just for our information. We want to save it for a while, but after that we want to delete off because it's just consuming extra space. So maybe a delete operation, but nothing else apart from that on this data structure. So now what our task is to see whatever data structure you are thinking of using. Your task is to mentally process this operation. Now use that data structure. Think of if you want to do an insert or a modify on that data structure. You already have some information there and some new flight request came. If you want to insert it, what will be the cost of that operation? Second, if you want to do a check in that data structure, right? You need to check if there is any flight schedule within +3 and -3 time interval of that new request. What will be the cost of that check? Versus if you want to also delete, what will be the cost of that? If you can come up with a data structure that has all 3 of this in best possible, like the least cost, then that's the best data structure. So we have some people replying on chat saying maybe we can use array or vector, could be more flexible. We have already discussed queue. Let's just jot them down. Let's just jot the options that we received from you until now. Queue, array, vector. What else? Sorted array. Okay, so these were the options. If I missed anything, please speak up. These are the options that we received by chat until now. And Rohan said queue before when we were discussing. So are you guys still on this on one of these data structure to be used? Do you still, after we discuss different operations, after you think of cost of these, each of these operations using this data structures, is there anything that we can rule out, or we want to consider everything? Girls and guys, if you don't speak, if you don't type, I don't have a psychology power where I can understand what's going on in your mind. I wish I did, but you got to speak and you got to type. Then I can read, or we can listen. Random access followed by sending the results back in time would be fastest algorithm. Technically, does Q have random access? Brian, I'm not sure, what do you mean by random access followed by sending the results back in time? If you can unmute yourself, that would be helpful so that we all can listen to you. Okay, I believe you are still thinking. So, okay, let's take each data structure one by one, and let's see how things could go. So which is the most basic data structure that we learned initially at the beginning of this class?
Array.
Array, or let's say unsorted list, right? Array and unsorted list are almost similar, where list have pointers to elements while array has index. But so if it's an array, then you have index for each element. So that index could be timestamp. You can convert your timestamp into something that's valid to become an index of the array. And that's how you can maybe identify, or that's how you can check, right? For an array, if you know that if it's an array A, if you know the index of the item that you want to check, let's say the item that I want to check is the third item, then the cost of check is just big O of 1. It's a constant cost. You just directly see if that item is there or not, and that's it, you are done. So insert in array, so the check can be a constant cost. Now, what about insert in an array? So for an insert in an array, if you are maintaining things, if you want to maintain things in a timeline fashion, right? Because only if you maintain things in a timeline fashion, then you will be able to do the check faster. Or because for the check, you also need to check one element after, right? If the third is an element that you're checking. But then because we have this constraint of k equals to 3, so you also want to check a of 4, and you want to check if a of 4 is greater than equal, at least greater by 3 minutes from a of 3. And you also want to check a of 2, and you want to check if a of 2 is at least lesser by 3 minutes from a of 3. That's what will do your check. And this is possible only if you have things in a sorted order, right? Otherwise, you cannot just say that a of 4 is something after a and a of 2 is something before a. So because of these constraints, if you want to store things in that sorted order, so every time in an array, if you want to insert something, then that item that we want to insert, like in this example, we are not going to always insert at the end of the time, right? We are not going to insert only after the latest flight. We don't know in which order the requests are going to come. Might be the flight that's the flight that's going to land at 10:35 that sent us the request like 2 days back that, hey, I want to schedule a flight to land at this airport after 2 days at this time and all. So that was there in our data structure, like right first flight. And then we got for 10:41. This was luckily after 10:35. But then these two requests, request 3 and request 4, they were not after 1041. It can be that your request can be anywhere in your timeline, and they just need not be in an incremental order of time. And because of that, now if you want to insert this item 3 and item 4 into your array here, then you might have to do something, some shifting, right? You might have to shift some elements and make some space. So your inserts might be costly if you are maintaining a sorted order of time. And how many items you want to shift, that depends on how many items are there after this timestamp. So in worst case, you might get a request that's the earliest timestamp from compared to all the requests that's already there in your data structure. And in that case, you have to shift, like if there are n elements in your data structure, then you have to do the shift operation for all the n elements, right? You can start from the last and then start shifting everything. Finally, that empty space when it comes to the beginning, and then that's where you do the insert. So your insert might cost big O of n. And your delete operation, in this case, you can just, if you want to delete the history, then you can just say that, okay, time lesser than equal to this, delete everything that's before that. So delete operation is, for one delete operation, you will, for one item, it's just a constant cost. But again, it depends on how much cost it takes to delete number of items. So if there are m items, then for each item, because it's single operation, then it might take big O of m. So these are your different costs. Now, is linear cost, linear insertion cost, the best thing you can do for this? Which is the most frequent operation you might encounter in this application?
Would it be check?
Check and insert, because every time you are checking, right, there are two things. Either you just print out that, sorry, we cannot, but if it's possible, then insert is always followed by the check, right? So check and insert are two. The check is the most frequent operation, right? First thing you do is check every time you get any request. And then for most of the check, you want to do, as for as many check as possible, you want to insert. For the check that have conflict, you don't have to insert. So number of check is the first most prone operation, but then second is insert as well. So in this case, if you maintain things in sorted order, check, we have like good with the, we are good with the check, but our inserts are something that is not that good. So let's think of some another options. If you are maintaining, if you don't maintain things in a sorted order, like here we assume that you are maintaining things in a sorted order, which could be also called a sorted array. But if you don't maintain things in sorted order, and if you just have this array where you are just inserting at the next index, you start from index 0, you don't have any like smart method of correlating your index with the timestamp, but rather whatever request you are getting, you are inserting in a first a of 0, then a of 1, and then so on and so forth. So here in this example, our a of 0 will be this, our a of 1 will be this, our a of 2 will be this, and our a of 3 will be this. So a of 3 won't be there because that flight won't be scheduled. We won't insert that. But this is how, if we just blindly insert things, in that case, what will be your check cost?
Would it be n for all items in the array? N occur constant cost n for, because you have to check every time in the, basically put every time in the array.
Correct. Yes, that's perfectly right. So because there is no sense of time, every time there is, whenever there is a new request, then you don't know like what to check for that, right? You don't know exact which location to check for that. And all the items until then is just entered in the request first come, first insert, that order. So you don't know exactly which index to check, and that's why you have to check all the items that have been entered until now. And if the items entered until now is n, then your cost for insert in this case, or the cost for check, sorry, will be big O of n. How about the cost for insert? If you
So
don't
big O of n,
maintain a sorted array, yeah, Aries, go ahead.
it's also big O of n.
Big O of n?
Unless you insert at the end, but like, okay, unless you insert at the end, you could do that too, I guess. Like inserting at the end, so just put it in.
Yeah, because if we don't have a sorted array, then you don't have to do any shifting, right? Because you don't have to do any extra efforts to maintain that sorted nature. And in that case, whenever a new request arrives, like here, when this new request arrived, right, the third request, what we did was we just added one more element. So you know that, okay, until a of 1 the array has, and then you added a of 2 as this request. So in this case, because you don't have that sorted new responsibilities to maintain the sorted order, the insert can just be done at the last element of that array, like until whatever is there, whatever element, until wherever the array is filled, you can just enter one more element after that. So the insert will just be big O of 1, not big O of n. And delete, well, that will be almost the same for all these data structures, right? Because delete is just at the time that's lesser than the timestamp that we want to delete, and then we go back and just delete everything that we have until now. So doesn't matter, the delete doesn't matter to us much. But then, as we know that the check is more prone operation, so now if you have to choose between a data structure that gives check at the cost of big O of n and other data structure that gives check at the big O of 1, then I would definitely choose a sorted array instead of a normal array, right? Because check is the most prone operation, and you want to be things more efficient for most prone or most frequent operation. So I would say let's rank. If we rank them, until now I would rank this 0, I would rank this 1. Our rankings could change. Let's use black color. Our rankings could change over time. Now let's evaluate. What do you want to evaluate, vector or list? Let's evaluate list, because list is a bit different topology than array, right? In list, when you are doing insert, then you don't have to shift all the elements. You can actually do just the pointer redefinition, as we saw when we were discussing list, how to insert an item in between the list and how to delete an item from in between the list. So we can do those steps, and then it is possible to insert anywhere in the list by just redefining the pointers of the item before that and item after that. So what about list? List, you cannot maintain sorted in a sorted order, right? Because list does not have any concept of index. So you cannot have like something equivalent to this. You cannot have like sorted list. But the best possible list you can have is just the normal list, which we can call as unsorted list, similar to unsorted array. But in case of list, as we just discussed, that if we use list, then our inserts can be big O of 1, because we don't have to do any shifting or anything. But what about check? What will be the cost of check operation if you store your items in an unsorted list?
Big O of n.
Big O of n, correct. And why is that? Eris, can you go ahead and explain that?
Because you need to go through every item, because you don't know if the last item might be the one that is like in the range that you need. So you need to go through all of them.
Correct. because you don't know where again to find the item, right? There is no concept of index in the list. So every time you want to do a check, you have to start from the first item. You have the head of the list, and then you do head next, 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 and then you check all the items that you have in the list and see if that the constraints are conflicted or not. Okay, so we didn't find anything better with the list. It's almost same as array. How about queues? Rohan, you mentioned that you want to use queues. Do
Yeah, I
you
don't
still
think you can use
stick
queue.
to?
I don't think you can use queue. I'm more in favor of sorted array now. I don't think
What's the
queue.
problem with using
Because
queues?
I assume that the first, like the time that the first time would be the first time in a queue, but that's not the case because you're checking the first one that you want to insert may not be the first actual time in terms of order you want the flights to land on the runway because of the buffering time and everything. So that's why queue wouldn't work in my opinion. I didn't consider that when I was evaluating when I said queue.
So
So
queue by itself is not sorted. So with
yeah,
queue, that's the problem,
yeah,
right? And again, you don't know what to check here. So your check operation will be
yeah,
big O of n in
mhm,
queue. But queue also has a variant of priority queue, which can be sorted if you give the priority in terms of timestamp, right? The priority queue can be implemented using heaps. We already saw that. And for heaps, the search operation in heaps is the heapify operation. The insert operation and the search operation in heap is way cost effective in terms of log n rather than the linear cost of n. And log n is more effective than the linear cost of big O of n. So if we think, what do you think if we use priority queue?
I mean, yeah, priority queue, if we're gonna maintain order and define the order being inserted as the timestamps, I think that would work. But for me, I think sorted array is just like, and for me at the moment, I'm in favor of sorted array at the moment still. I think that's just
Okay,
leaning towards that now. Yeah.
okay. So with the queue, normal queue, the problem is if you check, that's big O of n, you need to check all the elements. And if it's a normal queue, your insert will be always at the tail, right? So then the insert is same big O of 1. You don't have to do anything smart for your insert. In terms of priority queue, again, you're maintaining things in a sorted order. So you have that sense of timeline, right? And in that case, if you want to check in a priority queue, but you don't have as many features as checking in a sorted array. So priority queue, if you compare priority queue with a sorted array, what's the difference is array has index for each element, while in queue, you can just access the head, right? You can insert at the tail and you can access the element at the head. That's it. And head might not be the element that you want to check. Like when you are doing a new insert, that timestamp, the element that's after that timestamp and the element that's already before that timestamp, they might not be available at the head. So in array, you can, because you have index, you can check something like this and this, but in queue you cannot do all those operations. So for check in a priority queue, you still need to go through all the elements. So your check is big O of n, and your insert, because it is a priority queue, so every time you add a new element, it needs to shuffle the items inside it to maintain the priority. And we know that if we maintain a priority queue with a heap, then to solve one violation, that's what we call as heapify operation. So here all other items are sorted. When this new item comes, that's the single violation that will be made, and we want to solve that. And the cost of heapify operation is big O of log n. So that will be our cost of insert in this case. Well, this is even worse than just using a normal array. So definitely not priority queue. And I would say priority queue -1 rank. Queue as same as what was the rank of array and unsorted? It had 0, right? So 0 rank. Vector. Now that's the last thing to rule out remaining on our board. How many of you think vector is still a good idea to use? Who said vector? Brian said vector. Okay. So vector is nothing but a flexible array, right? The array in which you can add more element and delete the element. So you don't have to define the size of an array. That's the comfort that vector gives. But because of that property, vector is almost like an array. We can just group it with this class of array, right? We know that in a day, not more than whatever, let's say in a day, the traffic of this airport at max is landing 200 flights, and not more than 200 flights will ever be landed or taken off from this airport. So then you can just define an array of size 200, and you don't need to worry about the dynamic increase and the increase of the size that you need vector for. So vector is almost similar to array, and it will also have the operation cost similar to array. So even that's rank 0. Okay, so as of now, sorted array looks the best, but the biggest problem, what's the biggest problem with the sorted array? We already discussed it.
Inserting into the array.
Inserting into the array, right? So every time you want to insert, you have to shift all the elements, and that won't sound good when you have 200 elements scheduled after whatever timestamp the request is coming for. So you have to shift everything. So if we can solve that problem of sorted array in a better way, then we can, so then that data structure will be even good, more better than a sorted array to use for us. So let's say the key thought of what we want to do is fast insertion into our sorted array. This is the key that we want to achieve, or this is something that we want to do for this to solve this problem now. So now this links us to a binary search tree. Binary search tree is a data structure which is a breed of tree, as you already know. In binary search tree, what we store is some information about the node, right? That could be our key X or the timestamp. And then we have some pointers. These pointers are parent pointer, so parent of X, the left child pointer, left of X, and the right child pointer, right of X. Unlike heap, if you remember heap was visualized as a tree, right? When we drew heap, we kind of visualized it as a tree, but heap was actually stored as an array. So the definition of heap itself is an array visualized as a partially complete binary tree, or no, partially complete tree. So, but in the binary search tree, we don't have, so unlike heap, we don't have the array itself, but rather we have pointers to the left child, pointer to the right child, and some information stored in every node. So if you have a data structure like this, where you have these all information, right? And definitely, you know that binary search tree has some sense of something that's lesser and something that's greater, right? So it has some sense of sorting within it. And that's what is important to us over here. Like that's where from all these data structures that we saw, heaps, queue, array, vector, list, from all those data structures, we choose to go with sorted array. So sorting is something that's important feature to us. And we know that binary search tree stores information in some sense of sorted way. And now because binary search tree has pointers and not index, so we don't, if we want to insert something, then we don't have to do the shifting, or we don't have to go with that pain of shifting all the elements after that point of insert. And we can just modify the pointers as we do in linked list, and we can just like insert elements without much cost. So how would this happen? Let's say that we are making our binary search tree, and let's say that our first request came. Our first request was for timestamp 49. So we insert our timestamp 49 into our tree. When there is nothing, you just insert. Then our second request came, that was for timestamp 79. Now, because it is a binary search tree, when you insert 79, then you would definitely insert it as a right child, because 79 is greater than 49. And everything on the right should be greater than the node, and everything on the left should be lesser than the node. Your third request came for 46. So 46 lesser than 49, you insert it as your left child. And so on and so forth. Let's say your fourth request came for 41. And every time when you're doing an insert, definitely you're also checking, right? When you inserted 79, you checked if 49, that was the only element at that time. So if 49 was a conflict. But no, 49 is more than 3 minutes away from 79. So we inserted that. Again, 46, it's exactly 3 minutes away, 6, 7, 8, 9. So there is no conflict, and we inserted that. 41, if the fourth request is 41, so what we will do is definitely 41 is lesser than 49. So we will traverse to the left. Then we come here, 46. Now 41 is lesser than 46, and 41 does not have conflict with neither 49 nor 46. And that's why we will insert 41 over here. Now let's say we have, what do you want to take? Something that has conflict. Let's take example of that. Let's say we have 78. The fifth request is 78. So while you are checking for this insert, what you do is you definitely start from the root. So we check at 49. 49 does not have conflict with 78. That's good. And 78 is greater than 49. So we know we want to traverse to the right side of the tree. So we go over here. Then we check this element, that's 79. 79 has conflict with 78 because it's not within that plus or minus 3 range, right? It's just one minute away. So 78, because it has conflict with 79, we will just say that, oh, sorry, we cannot insert it. Is this process of using binary search tree and inserting and checking clear to everyone? What, do you have any doubts?
So because 78 is lesser than 79, it can't be on the right child, right?
No, we are also concerned about our constraint, k is equal to 3. So only if, so we will be scheduling flight only if it is not conflict with this constraint, right? So because 78 is not, it's just 1 minute before 79. So these two flights cannot land or take off at that time. And 79 was already pre-scheduled, right? So you cannot just go back in time and say that, oops, sorry, now I cancel. Once you insert in your data structure, once you say green check to the pilot, that's it, it's done. You can't go back and undo that. But what you can do is for the future request, you can say that, okay, because you already have the some requests that came before that point of time, you can say that, okay, there is, check those previous requests, and you can reply that, no, sorry, there is a conflict. So for 78 is a request that you got after 79. So you won't make any changes to your previously already scheduled request, but rather to 78, because it doesn't fall within the plus or minus 3 minutes constraint. For it to be scheduled, it needs to be either 39 plus 3 or 39 minus 3. and then you can insert into the data structure. That's just that the constraint comes from our problem that we are considering, the airport scheduling system problem. But if there is no constraint, then definitely you would insert this 78, or if the constraint is just lesser than 1 minute, then 78 is lesser than difference of 1, and then you can insert it over here as a left child of 79. Any other question?
I just wanted to kind of say something like in regard to the application of this. Like, I don't know, I just wanted to say something interesting. Oftentimes what happens is, let's say in real life instance in a runway, if there's 2 flights and one flight was already scheduled and one like the flight's about to land and another flight wants to schedule and there's no conflict in between, often the air traffic controller will say to the other plane, you can circle in the air for a certain amount of time. And then when this plane ends, we'll let you know when you can land. Just something interesting I wanted to say in regards to like how if the timing is close, how they address that. Something that's on.
Yeah, sure. So if that's the case, if you want to address in this problem, then what you would reply to the pilot of the flight number 5 is that, okay, we have something that's scheduled at time. You want to reply this timestamp. So we have something that's scheduled at this timestamp, but this +3, if you can stall for that much time in the air, if you have enough fuel for that, again, then you can land at what will be, it will be 82 seconds, right? So you can land at this time. That's the next fastest available slot. So yeah. Okay. So what will be the cost of insert in binary search tree now?
Log n.
Log n, think a bit more. What most of the time, if your tree is something that looks like a tree, then how many elements are you parsing when you are doing the check and insert? Our check and insert is like hand-in-hand operation, right? You can't insert without a check. So you do check first. If no conflict, then you insert. So to do that operation, how many elements are you passing by?
It's like one at each level, right? Like one at each level of the tree.
Correct. So when we were doing check and insert for item 41, right? The item number 4, we just passed through this half of the tree. We didn't pass through this side, the right-hand side. While when we were doing the check and insert for item number 5, the 78, then we just passed through this side of the tree, right? We didn't touch like this side of the tree. We didn't have to pass through those elements. So looking at this observation, we can say that if the height of the tree is h, that's h and not n, though they sometimes, in my handwriting, they sometimes look similar. So I'm trying additional effort that it doesn't look. So then the cost of check and insert in binary search tree is big O of h, where you know that h is definitely smaller than equal to your n. Correct? Can you say that your h will always be smaller than equal to your n, right? In worst case, it's equal to n, and that's the case where your tree is just one-sided, right? There is no other side nodes, but everything is just lined up like a single. That will make it a linked list. Your tree will be like a linked list, and in that case, it could be n at worst. But that's the least possible scenario. In most of the case, you will have something on both the sides of the tree, right? And so in most of the case, it will be lesser. If your cost is big O of h, then that will be definitely lesser than n. Does everybody understand this observation? Any questions on this observation?
My question is, so this h doesn't equal to n property was derived from a property of this binary tree, right? One of the properties, so that property itself is derived from like the overall definition of the height of a tree, basically, right? How it'll be less than equal to n. That's
Yeah, so if you're
Okay.
inserting, so in this tree, right, what is your n in this tree, in the example that we took? What is, this is just a very small example.
Yeah.
Even in this case, your n is 4, right? There are 4
Yeah.
elements in your
Four.
tree. But your h is, if you just start counting from 1, then your h is 3,
3. Mm-hmm.
right?
Yeah.
So, and this is very small tree, remember.
Oh yeah.
The trees can actually
It can be
go
really
much
big
denser.
and diverse. Mhm.
Yeah, and the denser it grows, because every time every node has 2 child, right? So every time you
Yeah.
insert a new layer, you are increasing number of elements in the power of 2 to the power something,
Yeah.
that level, right? So the benefit that you're getting from H is some 2 to the power benefit for a really like dense tree.
Mhm.
So your H is going to be like 2 to the power something smaller than the total number of
And those.
elements in the tree.
Mhm.
Yeah.
Okay. All right. Thank you.
So, okay. What other operations do we want to do on this tree? Let's say we have some another operations. We have some time left. So I think now all of you understand how can we actually put binary search tree to use, and how binary search tree is solving this problem in a better way in cost of big O of H, for check plus insert operation. Everything, all other data structures that we saw until now, for check plus insert, the best we could get was big O of n, right? For all these data structures. Even for the sorted array, the insert was big O of n. So check plus insert, because both these operations for this application, we are doing hand in hand. So that was still big O of n. But with the binary search tree, we were able to do it in a better cost, big O of h. But let's say that you have some another operations in this binary search tree. Or you know what, let's do this. I'll continue this in the recording that I'll upload. I want to discuss some another operations for this binary search tree data structure. Not that may or may not be applicable to our runway reservation system. I'll try to connect the operations to the best I can. But what I want you to understand is how you perform some another things, like how do you delete a node from a binary search tree? How do you insert some, we already saw how to insert things in between in binary search tree. So yeah, depending on where the node that you want to delete is, if it's a leaf node, if it has a single child, or if it has a 2 child, there is different ways that we want to follow. So I'll discuss those all things in our next. Okay, so what other operations can we have on a binary search tree? Let's say, for example, if there is a query that asks that what is the minimum node that exists in the binary search tree. So find minimum in any given binary search tree. Or let's say if there is a query like find maximum in a binary search tree, or there could be other operations like with some more constraints or more complex operations, like how many flights have, so in the flights runway problem that we are considering, there could be a query that, okay, how many flights are scheduled to land from nav, which is the current timestamp, until whatever some given time. Let's say from afternoon 12 o'clock, let's say if the current time is afternoon 12, that's nav, then the query could be something like, okay, how many flights are scheduled to land from nav until evening 5 p.m. and whatever our data structure needs to return an answer to that. So for these all operations, like, okay, let's take different operations one by one. So let's take the first operation, find min. So if you are given a binary search tree, in that if you have to find min, what will be the process of finding that? Definitely, because it's a binary search tree, so you have nice way of maintaining elements on everything that's on the left is smaller than the node, and everything that's on the right, that's greater, and that applies to all the nodes. That's where the smallest element where you will find is the leftmost element. So in any binary search tree, if you keep traversing to the left, so if you keep going towards your left, start from the root and keep going left, keep parsing to the left child, it's left child, it's left child recursively until you hit like the end, there is no more left child. That element, the last element where there is no more left child, that one is the smallest element. So just go left, go to left. So what will be the complexity of find min operation? So if you have a binary tree, what you're doing is just keep on going on. So this is like a binary tree which also has other nodes, right? It can have something like this. But what we are doing in order to find min is just take the left, just keep on traversing on the left child and the left child and so on and so forth. What will be the complexity of such a find min operation? You have to traverse the number of elements proportional to the height of the tree. And that's where the complexity will be big O of H. Now let's say if there is an operation find max. This should be straightforward. What do we do for find max? I think most of you have thought this, right? Yes, you have got it correct. To find max, you just go to the right. The rightmost element is your maximum element in any binary search tree. And similarly, again, when you keep doing that, so now to find max, what you are doing is you are taking this path, right? To find max, you are taking this path. And here, because there is only one child, and now this is the child that doesn't have any more left. So this is your max element. Again, the cost of this operation could be in worst case proportional to the height of the tree, right? In worst case. So in this case, we are not triggering the worst case because this node doesn't have any more right child. But in case if it's the worst case, it could be at max big O of H. The cost of find max big O of H. Other bit complicated operation, like what we were just talking about, like number of flights that will land until some time t. Let's call that operation. How do we perform such operation? Let's call that operation as rank. Let's define that operation as rank. And because until time t, you would need that t as an input, right? So let's call it as rank of t. What is this is a query to ask how many planes are scheduled to land at time less than equal to t. T is something, it could be evening 7 p.m., 5 p.m., something like that. So from now until then, how many flights are scheduled to land? If that's the query, and as we know that we have stored our information in a binary search tree, let's take an example of a binary search tree. 49, 46, anything smaller than 46, 43. Let's go this side, 79. Let's have some another couple of children's or leaf nodes, 64 and 81, 81, yeah. So if this is your binary search tree, in this that you constructed depending upon the flights that were already scheduled to land until now. So this is your time. And let's say now the time now is 34. And the problem is, the query that can come is from now, so from 34 until whatever time t, how many flights are scheduled to land. So it would be something like, what is rank of 79? So the flights that are scheduled to land from 34 time until 79 time, number of flights. That's what we want to find out. Or it could be something like rank of 46. So the number of flights from now 34 until 46, how many flights are already scheduled between these two times. So I think now the problem is, the operation is clear to everyone. How do we do this operation? Think. Any smart ideas? Okay, let me give you a hint to think further. So the hint is, let's say if you have some another additional information, let's say you have this additional information which corresponds to the size of the subtree. So leaf node, that's just one node by itself. So its subtree is of size 1. All the leaf node will just have 1. But this node, which is 46, that's the node itself and it has one more leaf node. So that subtree, this subtree is of size 2. And let's say we have that information stored with us, additional information stored with us. This subtree here, that's of size 3, right? Because it has the node itself and 2 another children's of that. While the root node is of size 6, because it has in total 2 children and then 3 grandchildren. So the root node has size 6 with itself, 5 children and itself. If you have this information with you, somehow available to you, then how can you find the number of flights that are scheduled to land at time t lesser than equal, at time that's lesser than equal to t? There is no single way to do this. And I believe by now with this additional information over here, many of you would have thought of different ways. Let's pursue one way of doing it. So logically, if you look at this information over here, right, this blob of all the information that we have, what do we see? Oops, sorry for that. Just a wrong click. So what do you see? You know that, okay, this at any node, you know how many total nodes are connected to this node because you know the size of that subtree. Now you know the size of the subtree for its left child, and you know the size of the subtree for its right child. Additional information from the binary search tree way of storing information is that you have is everything on the left is smaller than the node and everything on the right is greater than the node. Now, when you start your traversal from the root, then you want to find, so you're given time, t, let's say that time t is 79, right? So then depending upon whatever that time is, you want to find that timestamp and you start your traversal in order to find that timestamp. And while you are traversing, you want to take some steps. What you want to do is, if you traverse to the right, that means whatever timestamp you are looking for is larger than the root, right? So that gives you an intuition that if you are moving towards the right, then you are moving passing one node, which is at least there is one node that's smaller than whatever you are looking for, right? So every time you traverse to the right, you know, okay, at least there is one thing more. That is, at least there is one flight scheduled before the time of what I'm looking for. If you traverse to the left, then you know that Well, whatever time I'm looking for, that's still something that's smaller than whatever the current node is. And as you know, our problem is to find the flight number of flights that are scheduled to land before that time t. So the current node, like whatever flight that current node represents to, that won't be additional, because that doesn't lie less than equal to t. That flight corresponds to something that's greater than t, right? So you don't want to add anything. So this is one of the simple observation when you traverse to find the node. Now, how we do traversing is just based on comparing the value. It's normal binary search, right? You compare 39 with 49, 79 with 49. Because 79 is greater than 49, you move towards the right. If you are looking for 46, then you compare 46 with 49. And then because 46 is smaller than 49, so you move towards your left. And in the same way, you do the same thing. If you don't find the node here in this example, you find the node. But let's say that there is one more example, one more query that is asking for 43. Then you don't find the node in one step, but because then again 43 is smaller than 46, so you will again move towards the left of 46 again. So keep on doing the steps recursively to traverse. Every time you are traversing to your left, you are not adding anything. So you have this variable, which is initially 0, right? That variable is number of flights. And this variable is initialized to 0. Every time you traverse to the right, that means there is at least one flight that is scheduled before the time of whatever t you are looking at. So every time you traverse to the right, you add 1. Every time you traverse to the left, you don't do anything. Just leave it the same. This is one of the basic operation. So now let's say if we are searching for all the flights that are scheduled to land before time 79, then we traversed from this route towards our right, because 79 is greater than 49. Then we came here, we added 1. So now we know that at least there is one flight which is supposed to land before 79, and that flight is supposed to land at 49. Now at 79, we find our timestamp. Whenever we find our timestamp, then you know that everything that's the left child of that timestamp, right? The size of the left subtree, the size of the subtree that's lying on the left, that's surely smaller than whatever the current node value is. Everything on the left of this node, everything over here, will be definitely smaller than this node. And if the timestamp is this node, then the size of the left subtree, all those flights that are scheduled and that are lying here are going to be something that's scheduled before 79. Everybody is with me on this observation? Everything that's there, the size of the left subtree of whatever time we are looking for, once you find that size of the left subtree is all the flights that are scheduled before the current node's time. So everything that lies on the left are smaller than the current time. That's the 79. Then the time that's required, the t for us. And that's the reason once we find our node, then we are going to add the size of left subtree. And this is why we maintain that subtree information, the subtree size information. And this is how that information helps us, because then we don't have to do more traversals. It's just one step, search, and boom, we know the answer that yes, that's just a single addition operation. So here in this case, the size of the left subtree is 1, right? for this for 79. So we'll add that. So we added 1 for the traverse. So we added the size of the left subtree. There's something else that we are missing. What is it? There's something else we still need to add. For the people who are thinking, what we need to add is the component that's lying over here. Correct. So every time when we are moving towards our left, definitely we are adding 1 for that node, but additional information that we know is the size of any node's left subtree, right? Even the size of this subtree for this node, that is something definitely lesser than this node. And if this node is lesser than whatever we are looking for, then including this, everything is lesser than that node, right? So that's the reason what we are missing is adding the size of the left subtree of any node that from where we traversed left. So if we add that, that's 2. Correct? So that gives us 4 flight. Is this correct? Yes. If we look at the example, if you see what are the flights that are scheduled to land before 79, 1, 2, 3, 4. These are the 4 flights that are scheduled to land before 79. So let's do for 43. What happens for 43? Let's work for this example. So we'll start at the root the same way. 43 is lesser than 49. So this time, instead of going left, instead of going right, we'll go towards the left, which is the smaller subset of the tree. And now because we are going left, we know that the item whichever we find on the left are more smaller. So the item of the node itself, that's bigger. And we are just concerned with anything that's smaller than equal to t. So we have no concerns. Basically, we do nothing. We just traverse. We traverse to 46. At 46, we compare if 46 is, did we find 43 or not? So 43 is further smaller than 46. So we traverse one more step towards its left. And finally, we find 43, right? In this case, 43 is the leaf node. It doesn't have anything on its left or right. In case if 43 had a subtree on the left, right? In case if it had like a structure of nodes on the left, then we would have just added your answer of how many flights that are scheduled to land before 43 would be nothing but the subtree size. So 1, 2, 3, 4, 5 here. So that will be the subtree size on the left, because you know that those all nodes are definitely smaller than 43. So yes, this is how you traverse to the left. 79 is how you traverse to the right. Finally, let's look at how do we get the size of the subtree. Well, that should be a pretty straightforward counter maintenance. What we do is every time you maintain the counter for every node, you start traversing from the root. Initially, the counter is for the counter for the root is 1. When you do the in order, post order, pre order, whatever traversal you want for one time, just for one time to construct your size of the subtree array. And whenever you're doing that traversal algorithm, every time you go to the left child or right child, you increment the counter for all the nodes. So if you are traversing left from here, you increment the counter 1 + 1. You go here, you again initialize the counter. If you're traversing further left, you increment the counter for all the stages that's above, and so on and so forth. You can do the counter maintenance. Another way to do this in an easier fashion would be to start from reverse. So just traverse to the leaf of the tree, then say that, okay, the leaf of the tree has 1, the counter is 1. And every time you can go back to the parent of the tree. So every time you go up, you increment the counter for that node. You go up, then what you do is you take the counter for the child plus 1 for the parent, and then so on and so forth. If you traverse in that way from bottom up, you can maintain, you can do like that, but that should be easy to have that, to construct that additional information array which maintains the size of the subtree. And once you know the size of the subtree, then you can find out or answer the query like this one, that how many flights landed before t. As I said before, if you remember, there is not just one solution to this answer. There could be another approach where you, rather than the additive, you take more of like a subtractive way. And yes, that's also definitely correct. So if you have come up with some, if your mind has created this good, nice subtractive approach, it's different from this, that's definitely not wrong. And that could be another way of doing the same problem. What are some other operations that we can do with the binary search tree? Let's discuss delete, right? Delete is something which we might want to do. And here in this flight example, how we talked about delete earlier was more of like, if you want to delete the history, so you were just going to like, if the timestamp is lesser than this timestamp, then going to delete all the flights or free the memory for all the flights before that. But not all the time delete operation could be something like this. Let's say that we have a delete operation which doesn't concern with the history or clearing the space, but it's more of like the flight request was scheduled and we gave a green signal that yes, flight can land at that time. But there was some weather conditions at the place of takeoff. Let's say the place of takeoff was Boston to Miami flight. And in the month of November and December, because of heavy snow, the Boston flight takeoff was delayed. And because of the delayed takeoff, now the flight is not going to land at the same time, which we scheduled to land at Miami airport. And because of that, now you have to delete that. Like, because they said, oh, this flight is canceled because of sudden heavy snow or slippery runway condition. And so initially the request was scheduled, it went through, you gave the green check, but later, due to some uncontrolled circumstances, the flight was canceled. And now you have to, in your array, you don't want to occupy space for that, because there might be another flight that want to come from somewhere else, for example, Houston to Miami, and that route is good enough. And it might want to land at the same time. So you want to empty that time. So in that case, you might have to delete some nodes from the binary search tree and delete a particular node. Now, there are different cases and where this node could lie. So if this node is a leaf node in your binary search tree, if it's a leaf node, that's what you want to delete, then how would you delete it? Let's say you have a binary search tree. Let's make it a different tree. Let's give some new numbers. 5, 2. I started with 5. That's a really small number. Okay, let's consider that we can go negative. Then you have 3. This side is a wide opportunity. We can have how many ever numbers we want. Anything greater, 25. Okay, so, and yeah, maybe 20. So this is the binary search tree, right? Left of all the nodes is smaller than the node, and right of all the nodes is greater than the node. Yes, it's a binary search tree. This quick scan of NI. So in this binary search tree, let's say we want to delete the leaf node. Let's say we want to delete this node over here. In that case, what we would do, we would just parse to that node. Now, by this time, everybody knows how to traverse through binary search tree, right? Just the binary search, the usual binary search that we do. So we will start from the 5. We will say that, okay, if the element that we want to, if the command that's given to this data structure is delete 20, then because 20 is greater than 5, we'll traverse to the right. 20 is greater than 12, we'll traverse to the right. 20 is smaller than 21, that's where you'll traverse to the left. Now 20 is greater than 19, so you'll traverse to the right. And yes, hooray, we found 20. As soon as you find this element, whichever you want to delete, if it's a leaf node, then doesn't matter, just delete it, right? Go ahead and delete, doesn't matter. So in this case, you can just delete off the node 20, free the memory space that's occupied by that node, and that's it, you're done. But not always life is so easy, right? So let's say that if there are chances that the delete command is not for the leaf node, and the delete command is for the node that has one child. In that case, what do? Let's say the delete command is for the node that has one child, which is the node that has one child over here. I guess this is the only one. Everything else has 2 children. So if you want to delete 19, if that's your command, what do is definitely first traverse to 19. I'm skipping that steps of traversal. Now that once you have traversed to 19, once you have found that, oh yeah, I have found the node that I want to delete, then you cannot just like delete this off, right? Like what you did with the leaf node. Then in that case, this node that's child of that node will be stranded, and you don't want any child to be stranded, not even in trees, not even in computer science trees. Definitely not in computer science trees, because then such stranded items will lead to just occupying your memory, and you don't have any way to reach to that. And that's like one of the big persistent storage problem. And most of the time, if it's the DRAM where this thing is stored, then you have to restart the system. So if you restart the system, the stranded memory, it gets deleted, because everything in DRAM gets deleted once you restart the system. But if it's the persistent memory, right, then you cannot even, if it's the persistent storage, anything that's persistent, you cannot even delete it by restart. And then how to find that? It's like no way to find that. And there are some ways, obviously, but it's a big pain problem in computer science. So you don't want any stranded items anyway. If you don't want a stranded item here, then how you would delete? Well, in that case, there's an easy workaround. What you do is, before deleting 19 and just making 20 stranded, whatever is, because if this is the node that has one child, then you can connect that child to the parent of whatever node you are deleting, right? Every parent has 2 children. And so the parent of the node that you are deleting, which is this node, it needs to have 2 children. If one of the child is what you are deleting, and if you connect its child, which you are sure that it has only one child, that to the parent, then you don't violate the property of binary search tree. Still, all the nodes will have at max 2 children, and everything on the left will be smaller than the node, and everything on the right will be greater than node. So simply just delete that. But before deleting that, do connect the child to the parent. Do connect the child of the node that you are deleting to the parent of the node that you are deleting, and then delete that. So if we do that, yes, there is no problem. And our binary search tree will just look like something like this, which is still a binary search tree. So that's fine. But now the bigger problem, let's say the node that you want to delete, let's make our life a bit harder. The node that you want to delete has 2 children. Then in that case, you cannot do the same thing that you did while deleting the node with 1 children, because in that case, what would happen is, let's say if you want to delete this node, right? Let's say if you want to delete 12, and 12 has 2 children. If you want to delete 12, and if you just connect the child, if you just connect both of this, the child of 12 to the parent of 12, then the parent of 12 will have 3 children, right? This will have 5. It used to have 12, but later if you do the same step, then it will have 9, and it will have this 21 and all the subtree that's related with 21. And that's something that will violate the binary search tree property. So that's something that you cannot do. What else that you can do? Some of you would have thought this. Okay. So what you want to do here is look at the element that is, replace the elements that you want to delete. So replace this element with the element that is just element that's a part of this subtree. And if you replace this with that element, it wouldn't violate the property. Replace it with that type of element. Where you can find that? You can replace this element with 9, right? You can replace this node with that. Then in that case, you'll have 9 over here. And everything on the left is smaller, everything on the right is bigger. That wouldn't be a problem. But in that case, if this had a subtree, right, then it may be an issue to replace that. That might not be possible. So the safest way to replace this, to find such a candidate, is to replace it with the minimum element in the right subtree. So if you traverse the right subtree, if you go to right subtree, in the right subtree, the minimum element that you find, where you will find that is the element at its leftmost child, right? In this case, the minimum element is not 20, the leftmost child is 19. So if you go to the minimum element in the right subtree of the element that you want to delete, and if you replace that element with the node that you want to delete that has 2 childs, so if you replace this with this, if you make this node as 19, but when we make that as 19, because we cannot have 19 at 2 places, right? So we need to remove the node from here. So in that case, if you want to remove 19, you'll follow the delete procedure in a recursive way. So if you want to delete this, then you will follow the procedure, because this has 1 child, you will follow the process of deleting a node with 1 child. So you would replace 12 with 19, but then you still have to delete this node over here. Following the process of deleting the node with 1 child, we'll just connect 20 over here. So in this case, now let's look at the tree. Every node has at max 2 children, right? That's not violated. Every node's right side is greater, and every node's left side children subtree is smaller. So yes, this is a binary search tree without any violation. And this is how we can delete the node with 2 children. We also call that element, like with the element that we replaced over here, we also call the element in the right, the minimum element in the right subtree is also called as in order successor. In right subtree. So sometimes you might come across this term in order successor. In order is nothing but L and R, and the minimum element in that right subtree is also popularly called as in order successor. So if you replace, if the node has 2 children, and if you want to delete that node, then replace that with its in order successor. And in the process, if there are other deletions that you need to do, then follow recursively the process of deletion. The process of deletion for the leaf node is one thing, for the node that has 1 child is a way, and the node that has 2 child has its own way. So just do that recursively until you reach a state where your binary search tree is still valid, nothing is violated, and you have deleted the thing that you actually wanted to delete. So that's it. So these are different operations on binary search tree, and binary search tree is again very useful data structure, especially for scheduling algorithms. It's used popularly in at different places. So if you have any questions on any discussions that we did on binary search tree, feel free to email those to me, and see you in the next class, in the next module. Bye-bye.